do the introduction, please?
I can indeed. Good evening, Sarah.
Hey.
This is a short piece that you should recognise perfectly well because I took it off your website.
That's fine.
It starts off, I'm an observational astronomer with research interests in white and brown dwarfs. I have published research on topics as diverse as the first T-dwarfs in the Pleiades, the white dwarf initial mass final mass relation, and new L-dwarfs in Blanco 1, the Hyades and Praesepe. I'm currently researching brown dwarfs in close binaries with white dwarfs, and I'm investigating excuse me, how the atmosphere of the brown dwarf changes with irradiation. I began my STFC Ernest Rutherford Fellowship on irradiated brown dwarfs in January 2019. I am the LSST person to contact for the solar neighbourhood in the UK, and I lead the aerial working group on brown dwarfs. So can please everybody welcome Dr. Sara Casewell. Thank you. Over to you, Sarah.
Hey, okay, so I'm going to share my screen. Let's hope this works. I've done this recently, but not in PowerPoint. So let's see how we go. PowerPoint. Sure. Please feel free to interrupt and ask questions as I go. But yeah, I'm going to talk to you a little bit about white dwarf stars, which are pretty cool objects, both, well, not that metaphorically, but and hopefully pass on some of my enthusiasm for these objects to you. So yeah, I'm a research fellow funded by STFC, who's the UK funder for astronomy mainly. And that basically means I have 5 years to work on my research project at the University of Leicester. Okay, so now this is where, okay, yeah. So I'm an observational astronomer. So I'm sure you are all familiar with what that means. You might not be familiar with some of the tools that I get to use. So we have telescopes here that are around the world. This one at the bottom in the middle is Gemini North on Mauna Kea, and that's me during my PhD a long while ago now. Stood underneath UCURT, which was the UK infrared telescope on Hawaii, and it's me filling the instrument at the Isaac Newton telescope on La Palma. So our instruments are normally cryo-cooled with either liquid helium if they're infrared, or liquid nitrogen if they're optical instruments. And the Isaac Newton telescope has to be filled twice a day for the CCD, and it's normally the student's job to do it. So that was what I was doing there. Here at the bottom, can I just check, you can all see my mouse, right?
Yes.
Good. Here at the bottom is what it essentially looks like when I go observing. So these screens, Wolfcam, the camera I was using, has four CCD chips. So I have a screen for each CCD, and then the other two computers do real-time weather and the telescope queue, which is part of my job as the observer is to select what the telescope observes next. If it's a queue-scheduled telescope, we don't always get to observe. We don't necessarily get a night to ourselves on all telescopes. You go out there as an observer, and while it's nice if you can observe your own stuff, quite often you're there to run the queue and to select what the best objects to observe based on the weather conditions and whether they're rising or setting, etc. is. I don't just use ground-based telescopes. Some of you are going to be familiar with what you see here. So in the middle at the bottom are the 4 VLT telescopes in Chile, which sadly are not observing at the moment due to the COVID-19 situation. There is Hubble, which, believe it or not, is 30 years old this year, which, yeah, I struggle to believe that one, quite frankly. And this you may be less familiar with. This is the Spitzer Space Telescope. So Spitzer was turned off earlier this year, and it's a 50 centimeter telescope in space, but it's primarily a mid-infrared telescope. So it observes at sort of 3 microns up to about 24 microns in sort of the thermal infrared. So you might think not that good for white dwarfs, but I will explain a little bit about why it can be very good for white dwarfs later on. All right, so white dwarfs, as you all know, are the end point of stellar evolution. They are what happens when a star, most stars, like 99% of stars, die. And they become this Earth-sized, very hot object that sit in space. And once they form, they simply cool and fade. I'm going to have to move my, there we go. So this is an actual image of Sirius. This is Sirius, the star you are used to looking at in the night sky. And this tiny dot here is Sirius B, the white dwarf companion to Sirius that you can't detect with the naked eye. It's too close to Sirius, which outshines it massively. So this is a Hubble Space Telescope image of Sirius and Sirius B. And again, you've got a white dwarf here in the middle of Planetary Nebula. So when your white dwarf forms, you're left with your Earth-sized lump of what was the core of the star, and the whole envelope of the giant star is blown off, and you get these pretty planetary nebulae. There we go. So this is sort of their canonical Hertzsprung-Russell diagram, what we're used to looking at for stars. You've got the hot objects up at the top, the O and the B stars, the blue things, and you at the bottom you have your red dwarfs, your M dwarfs. And our sun is quite nicely plonked in the middle there. And when objects start to run out of fuel, they effectively they evolve off the main sequence and they become a giant or they become a supergiant. And eventually that giant gets rid of its envelope and you're left with a white dwarf. So you can see, looking at the bottom, which is temperature, that quite often white dwarfs have the same temperature as O and B stars, but they're so much fainter. And that's because of their physical size. They're Earth-sized, not umpteen times the size of the sun. So until recently, this was what we went on for stars, and we would measure their luminosity based on perhaps model radii for the stars, and we'd plot a color magnitude diagram based on what we knew about stars and stars in clusters. Now, obviously, since last year, Gaia Data Release 2 came out, and Gaia has measured the positions of every single star in our galaxy, which is incredible. And we have this, which is exactly the same diagram, but with actual measurements. So these are what Gaia has measured for our galaxy. And you can see they look pretty much the same. We've got the giant branch up here. We have the main sequence, and the white dwarfs are over here. And we have there's some additional wibbles to do with objects that are becoming white dwarfs. These are the hot subdwarfs and other things. But yeah, the white dwarfs sit down here at the bottom. Now sorry, I'm moving my pictures of you all around so I can see what's on the slides. Right, so across the bottom, you'll see it has Gaia BP minus RP color, and this is what we tend to work in as opposed to temperature. But effectively, this is, BP is the bluer filter, the shorter wavelength, and RP is the redder filter, the longer wavelength. So BP minus RP, it's a proxy for temperature. And you can see the white dwarfs have measurements of about somewhere between 1 and 0, and maybe even less than that, because the brighter a star, the smaller the number for its magnitude, because it's the wrong way up, right? So white dwarfs, while they have an absolute magnitude of 10 in G, their BP minus RP can be sort of -1, because the blue magnitude is 10, but the red magnitude is 11. So we end up with this negative color, and we tend to talk about these objects as being blue objects. White dwarfs in general have spectra, when we actually look at what they look like across all wavelengths, they have spectra that are effectively black bodies, and a black body emits exactly what it absorbs. So it appears black at room temperature. And all you really, I know there's an equation that you don't really need to stress about, but the only thing you do need to worry about are the curves, is what happens to the peak of the curve. So the hotter your object, the further to the left, the further to the shorter wavelengths the peak is, and the higher it is. So if you've got, this is sort of sun temperature, if you like, 5,000 Kelvin, peaks here. But if you're looking at an M dwarf, a red dwarf, 3,500, 300 Kelvin, that peak is shifting towards the longer wavelengths. So most white dwarfs are a lot hotter than this, and they have a spectrum that looks remarkably like a black body, but there are some differences due to what's in the atmosphere of the white dwarf. Oh, I keep doing that. I keep pressing my my key button and it doesn't work with the screen sharing. So when we actually look at the white dwarf, this is one I've just pinched from the Sloan Digital Sky Survey website. You get this mess. So all of these atoms here that it's telling you are things that Sloan looks for to identify things. It has an auto-identify, so it picks stuff out and says, oh, that's a star, that's a galaxy, etc. These are the things it's looking for. But you can see that in the spectrum, you've got the black body shape, and then you've got these huge gaps, which are the hydrogen lines. So this one is H alpha, this one is H beta, and you have H gamma and H delta. These are called the Balmer line series for hydrogen. Most white dwarfs look like this. They're what we call a DA white dwarf, and we only see hydrogen in their atmosphere. So the black body peak may be higher, and because the white dwarf may be hotter than this one. But in general, they pretty much all look like this. So these lines might be broader than if you've seen stellar spectra before, or take stellar spectra. These lines are probably broader than what you might have seen, and that's because of the high gravity within the white dwarf. You can imagine that a white dwarf is very dense. So it's physically very, very small, but the average mass of a white dwarf is 0.6 times that of the sun. So you've got a lot of mass that you're cramming into a very small space. So it's very dense. So all your atoms are bouncing around and the electrons are bouncing around, and you've got a high pressure. And because of this, you're getting lots and lots of collisions, and that's what causes these lines to be so broad. So this is a spectrum of a white dwarf that lives in Persepi. Sorry. And white dwarfs in open star clusters are really good places to find white dwarfs. We tend to find massive white dwarfs in open star clusters because in general, they're not old enough for the solar mass stars to have evolved into white dwarfs yet. So this over here has about a mass of 0.8 times that of the sun. And it probably came from a 3.5 solar mass star. So these are massive stars that have evolved already into white dwarfs. But you can see again, you've got this massive broad line, and the little peak in the middle here, which is the hydrogen. So this is effectively what we measure. When I take a spectrum of a white dwarf, this is what I get. You can see I've chopped them out, and it looks like a weird Christmas tree. And I compare these to a model, and I determine from the model what the effective temperature and the gravity of the white dwarf is. And I can then compare it to models like this. And now we have Gaia, we have the absolute magnitude because we have the distance as well. And I can start to figure out what is going on with the white dwarf, what's its mass, what's its likely radius. And that means I can then use it to help me find out about other objects that might be in binaries with white dwarfs. So white dwarfs they're incredibly interesting in their own right, but they're also really useful to tell us about other things because their mass and their radius is so well defined. And in general, they don't do stuff like stars do that make them difficult to observe. They don't tend to have star spots. They don't tend to pulsate. They don't lose mass. They don't do weird stuff that makes life really, really difficult. There's no flares. So white dwarfs in binaries with other stars are really excellent systems to look at to tell you about the other star that might be really hard to observe. So here you go. So these are effectively what I measure if you're interested in the parameters. So I've got the luminosity, which depends on the radius of the white dwarf, and the effective temperature. And this is the thing I'm measuring. And then the gravity of the log G depends on gravitational constant, the mass of the white dwarf, and the radius of the white dwarf. So I can combine these and work them back to get out the parameters that I need. There are lots of types of white dwarfs, but mainly most white dwarfs, as I said, are DA white dwarfs, like 80% look like this. You don't see anything in them other than the nice bumpy hydrogen lines and a continuum that looks a bit like a black body. The next step down, 16% of white dwarfs are DB white dwarfs. So these are helium-rich white dwarfs. These tend to be low mass because something's effectively happened to them to mean that they've lost all the hydrogen. You know, hydrogen is like the most common element in the universe. So to have a white dwarf that only has helium in its outer atmosphere, it has to have lost all its hydrogen at some point. There's then a whole collection of weirder white dwarfs, DBAs, so they have a bit of hydrogen, a bit of helium. They tend to be very cool. DCs are completely featureless, so they are just a black body, nothing else, no absorption features at all. They're extremely useful in terms of calibration objects. We quite often tend to use these as calibration standards for telescopes because there's no lines to stress about. So they're great for determining your the amount of water in the Earth's atmosphere, or the shape of your CCD response function. DC white dwarfs are great for that because there literally is nothing there. They are just a straight black body. DZ white dwarfs, I'm going to talk about a little bit more in a minute. These are white dwarfs that are polluted by metals. So these can be internal metals or external metals. And I'm going to talk about that a little bit more in a minute. And then we have other objects. So this one here is a magnetic white dwarf. So you can see the hydrogen lines look a bit weird. They're really broad. And this is because there's something called Zeeman splitting going on within the hydrogen lines. So instead of having a nice peak like this, you've almost got like a little W, because you don't get the sharp peak, you get 3 little peaks due to magnetic splitting. So these have very, very high magnetic fields. And they are horrible, horrible objects to work with. But they're also thought to be, they're generally very high mass, and it's thought that what they probably are is a merger of 2 stars. So the 2 stars have evolved, and at some point they've interacted enough to merge together. And this is why you have this abnormally high mass white dwarf. And I'm talking sort of 1.2 solar masses near the Chandrasekhar limit high mass. And also why they have such a high field, a strong magnetic field. All white dwarfs have quite strong magnetic fields, because if you imagine your star has the magnetic field, and then as the star shrinks to become the white dwarf, all those field lines, if you imagine a bar magnet, you know, with the field lines that go from the north to the south pole, they basically all get squidged together. And the tighter together your field lines get squidged, the higher the magnetic field. So this happens anyway when the white dwarf forms, but these properly magnetic ones with the Zeeman splitting are crazy, crazy magnetic. So there's definitely something odd going on there. And the last one, next one down is a cataclysmic variable, which you might be familiar with. Objects that you have a white dwarf, again, it tends to be a high mass white dwarf, sometimes magnetic, in a close binary with a main sequence star. And the main sequence star is losing mass to the white dwarf. So these are quite often in binaries of like 80 minutes, 90 minutes, very, very short period binaries, which you can only do because the white dwarf is so tiny. You can't get around like the sun in 90 minutes. It doesn't work. Your Hubble goes around the Earth in 90 minutes. So this only works because the white dwarf is so physically small. But the star with the white dwarf has got a little bit too close, and it's losing all this mass onto the white dwarf itself. And these sometimes outburst as nova eruptions. If you look out for nova and brightenings when you observe. And the last object is a white dwarf main sequence star. I think this is an M dwarf. So it's a DA white dwarf, white dwarf, white dwarf, white dwarf. And then when you get to about here, which is about 1 micron, you can see you start getting other features, and that's because at the longer wavelengths, your redder object, your M dwarf, which is cooler, is brighter than the white dwarf is. And if I have time, I'm going to come back to that when I talk about brown dwarfs a little bit later. Okay, so the metal polluted white dwarfs I find particularly interesting. And this is because you have so many options. White dwarfs are great because they have quite clean spectra, that you have all these options as to what you're looking at if you look at the white dwarf atmosphere. So if there are metals present, you have 3 options. It can be nothing to do with the star. It's a cloud of something between you and the star. So what we would call the interstellar medium, the ISM. So this allows us to study the local bubble, sort of weird bubbles of gas that hang around in our galaxy near to the solar system. Or the metals may be photospheric, they're in the star. So you can imagine this happens with the hotter, newly formed white dwarfs. You've had your explosion, you've got rid of your outer layers, you've formed your white dwarf, you've got your beautiful planetary nebula, and then all the other stuff that sort of got formed from your carbon, nitrogen, oxygen cycle, you might have made a bit of silicon, all this sort of stuff, it then falls back into the core of the white dwarf. So you can detect this in the white dwarf atmosphere. And then after a certain period of time, once the white dwarf has cooled down, generally below about sort of 30,000 Kelvin, all this stuff, because it's heavy, it's heavier than your hydrogen or helium atmosphere, has sunk onto the core. And your final option is that the stuff is circumstellar. So the diagram, the spectrum you can see here, you can see where we've got these metals. There's some here and there's some here. And there's two spikes, two absorption features. One is deeper than the other, and they're not in the same place, which tells us that they're moving at different velocities. This is your redshift, blue shift. So they're moving at different velocities. And when you measure this and we measure the hydrogen lines, which we know belong to the white dwarf, you can then say, okay, everything that has the same velocity as the hydrogen is in the white dwarf atmosphere, and anything that isn't is stuff nearby. And this object in particular, it has metals in its atmosphere, but it has metals that are orbiting around the white dwarf as well. And these metals are thought to be from the remnants of a planetary system. So like our solar system, essentially, the white dwarf forms. When our sun becomes a white dwarf, our sun's going to expand to about somewhere between the Earth and Mars. We're not quite sure where yet. And all the planets, Mercury and Venus, they're going to get destroyed. If it doesn't destroy Mars, it's probably going to push it out when it explodes. And then all those rocks and bits of stuff gradually fall back onto the white dwarf that forms, and they pollute the atmosphere. So that's what we're looking at. The other option is it's perhaps been a gas planet with a rocky core, and the gas planet's lost, and we're now looking at bits of the destroyed rocky core fall back into the white dwarf atmosphere. So these are extremely interesting objects, and quite often have dust disks, which we can see in the infrared. That's what you see here. So these tend to be very, very cool objects, because if they're not cool, the white dwarf is too bright at longer wavelengths for us to detect the stuff properly. But these wavelengths here are from Spitzer, that tiny little half-meter telescope in space. And it detected all of this, and this huge silicon feature at 10 microns. And this was detected sort of early on in Spitzer's lifetime. And the sad thing about this is that MIPS and IRS, because they're very long wavelength instruments, they ran out of coolant, they ran out of helium. There's only a finite amount of helium you can send into space on your tiny telescope. And it ran out of coolant. So we had to turn those instruments off, and we've not been able to observe this region of space in wavelength since. And we won't be able to until James Webb launches. So this is, and since this object, we've found so many more that we think look like this and have these disks and these remnants of planetary systems, but we literally do not know what's there until James Webb is finally launched and we can see what it reveals about these objects. So that's extremely exciting. I'm less keen about the fact that the deadline for proposals is going to be the 24th of November, and there's a high chance I'm still going to be homeschooling my children at that point, but we'll see how it goes. Okay, so why else are white dwarfs interesting? Well, they have this very defined mass radius relation. And this is because white dwarfs are held up by electron degeneracy pressure. So what this means is, because white dwarfs, they're not burning anything like a star. A star burns stuff in its core, and that stops gravity from squidging it together. With a white dwarf, it's not burning anything. So what's happened is the core has contracted and contracted and contracted, and it's effectively got to a point where it can't be squished anymore. And this is because of the electrons. Electrons are negatively charged, and this means there comes a point where you can't shove them together anymore. A bit like two magnets with the same pole. I look at my son's Brio train set. You try and put two of the magnets the wrong way together, then they repel. this is the same sort of idea. So you try and squid your electrons together and they basically get to a point where they go, no, it's not happening, it's not happening. And that's enough to hold up the white dwarf. And that's generally why they're all about Earth-sized irrelevance of their mass. So there are slight differences. More massive white dwarfs are slightly smaller, physically smaller, because they're denser and you can squidge everything a little bit more. But they're all about Earth size because of this electron degeneracy pressure. This is quite a well-defined relationship. The only thing we don't know is how thick the envelope that sits on top of that very, very dense core is. And we know this is mainly hydrogen, sometimes it's helium, but we don't know how thick it is. And that's essentially what we were trying to measure here. This is some work I did with my PhD student. And he observed very well-known white dwarfs, some of which you may have observed. I don't know if you recognize any of the names here. There's phase 24, Sirius B, Sirius A and B were here, Procyon was here. And what we did was we measured them to try and determine their mass and their radius, looking at very high resolution spectra with Hubble Space Telescope of these white dwarfs to try and determine whether they have thicker or thinner layers of atmosphere. And basically the answer was we couldn't tell, because observing these things is really, really hard. These are all in binaries. So what we've done is we've put, Hubble has, I should have thought about this and done you a diagram, but Hubble essentially has, it holds its pinhole for the spectra on like 4 crossed legs like this. And what we did was we oriented the telescope so we could stick a leg in front of the star. It's called an occulting bar. So we stuck the leg in front of the star so we could directly see the white dwarf. But it's not always ideal. And sometimes if you get spilled out light from the star around the edges, then it contaminates the spectrum and it makes life difficult for you. So that was that. But the data we're getting is still a heck of a lot better than anything else we've been able to do before. And Hubble is still the only telescope we can do this with because it observes in the ultraviolet. And we can't observe from the ground the ultraviolet, which is a good thing, because ultraviolet radiation, as you know, is terribly bad for us. It's really not a good thing at all. But Hubble is currently the only telescope that can observe at these very short wavelengths. And there is no telescope plan that's going to do that once Hubble dies at the moment. So that is something we are trying to persuade people to look at, that the ultraviolet is super important and we can't lose this capability, but we have to wait and see what the powers that be say. Okay, so white dwarfs, bearing this mass radius relation in mind, white dwarfs are super useful in binaries. So this is a white dwarf in a binary with an M star called NN Serpentis, which you may have heard of. And it's an eclipse. So this is your white dwarf eclipse. If you're familiar with planetary eclipses, you'll notice that one, this is very deep, because the M dwarf completely goes in front of the white dwarf. If you have something that is a few times the size of Jupiter versus something that's Earth-sized, you can imagine that, you know, your big thing is going straight in front of the white dwarf, and it goes completely in front of the white dwarf. And the eclipse doesn't last very long at all. We're talking a few minutes compared to, you know, when you look at exoplanets, you're looking for like a 1% bucket on a stellar light curve, and that bucket might last 2 hours, 3 hours. This probably lasts about 10 minutes max. And it's a total eclipse. The white dwarf is completely covered. But in a way, that's fantastic because we can measure the brightness of the M dwarf, which gives us an absolute measurement of the star. If we know how long the eclipse lasts and how wide it is, and you have this, here's the secondary eclipse. So this is what happens when the white dwarf is in front of the M dwarf. So you get a little bit of a dip, but not a big dip. You can absolutely calculate you can basically solve the system. You can get the motions of both components. You've got the orbit, you know how big they both are, you know how massive they both are. You know everything you need to know about the binary to understand the binary. And my collaborator, Stephen, did this for a bunch of M dwarfs and white dwarfs and came up with this. So this is the mass radius relation for M dwarfs. not white dwarfs. You use the white dwarf mass radius relation to get the one for M dwarfs. And this is actually really important. M dwarfs are really, really hard to measure. They flare, they're active, they are a complete nightmare. And they're also the stars that everybody at the moment wants to find planets around, because if we're going to find an Earth in the habitable zone of a planet, it's going to be around an M dwarf, because in general, we're looking for planets that are moving in front of stars. And if you're looking for a very small planet, you can imagine it's going to make a much bigger dip if it's moving in front of a smaller star than if it's moving in front of a massive great star like a G star. And because the M dwarf is smaller, you also get more, the orbits tend to be smaller, so you get more eclipses. Yeah, it's wonderful if you find something that looks just like the Earth, but you do have to wait an entire year before it eclipses again, before you can confirm that's what you've seen. So M dwarfs are hot property at the moment in terms of looking for planets that might be habitable. The problem with them is they're a nightmare to observe, but also you can see here, particularly at the higher mass end, they don't really seem to fit the straight line, which is the model. And in general, they seem to have physically bigger radii than all our stellar structure models predict, and we don't really know why. It might be that they rotate faster than we're predicting, and so they're bulging a bit like Jupiter does. It might be that they're more active, and this is throwing all the measurements off. But the best way to try to calibrate this relationship for M dwarfs is to find as many as you can in eclipsing binaries with something that you're sure of the parameters of. So if you can find loads of M dwarfs in eclipsing binaries with white dwarfs, then you can get a really nice calibrated mass radius relation. And no, it might not fit your models, but you do have a relationship that works. And because if you don't know the mass and the radius of your M dwarf, then the assumed parameters you come up with for your planet will be completely wrong, because you're measuring the ratios. You're measuring the ratio of the sizes. So if you don't understand the radius of your M dwarf, you're not going to understand the radius of your planet. Okay, so this is my last sort of fundamental relationship for white dwarfs I'm gonna talk about. And this is the very snazzily named initial final mass relation. And effectively, this is the correlation between the mass of the star and the white dwarf that it's going to become. And it provides limits as to how much gas is returned to the interstellar medium at the end of the star's life. So you have all your stars, or most main sequence stars, and eventually they're going to become a white dwarf after forming some sort of giant, not necessarily a red giant. They might have been on the asymptotic giant branch. They might have been any other type of giant, and then they get rid of their outer envelope to form a planetary nebula, and you're left with your white dwarf. And again, going back to the sun's going to become a white dwarf of mass about 0.6 solar masses. So it's losing about 0.4 solar masses, almost half its mass, just into space around the solar system. So the interstellar medium, the initial final mass relation helps to define how much mass we think stars are returning to the interstellar medium. And it sounds quite an odd concept, but realistically, this is actually really important, because everything that gets returned into the interstellar medium is then available to create new stars. So when we're looking at new stars that are forming and how much metal they have and all this sort of stuff, this is coming from what the dead stars kicked out, basically. So the upper end of the initial final mass relation also constrains the mass of stars undergoing type 2 supernova. As you might imagine, there comes a point where you don't form a white dwarf anymore, you form a supernova, and then you have a neutron star or you have a black hole. Now, the problem again with modeling this is that giants are also really awkward beasts. I mean, you'll all have seen the stuff in the news about Betelgeuse, and we didn't understand why it was dimming, and it's really confusing, and what's it going to do? Yeah, giants are a disaster area for modeling. They are big, they're wobbly, they pulse, they lose mass, they have winds, yeah, absolute disaster. Glad I don't work in that area. But essentially, because it's really hard to model the giant phase, we can't get accurate models that step all the way through from star to end of life to white dwarf. We can model the white dwarf really well. We can model the stars pretty well. We can't do the bit in the middle. So what we need to do is find out a way of figuring out what the initial mass of the white dwarf was. Now, this is sort of easier than you think because we have lots of white dwarfs in star clusters, and you know the age of a star cluster. So what we do is we look for white dwarfs in star clusters, and we know the age of that cluster has to be the total age of the white dwarf. So we measure the mass and the temperature, and we can use models to get the cooling age of the white dwarf. So this is how long the white dwarf has been a white dwarf. Bear in mind that once they're formed, they simply cool and fade away. So it's just a simple radiative model based on the size of the white dwarf. And once you know how long it's been a white dwarf, you can subtract that from the cluster age, and that tells you how long it was a star for. And then you can work backwards and use the model to find out what mass star it came from. Now, that sounds easier than it is because clusters have different metallicities, they have different ages, the age estimates are not always reliable, they have weird nebulosity that can cause you all sorts of hassle when you're trying to find your white dwarfs. Some of the white dwarfs you find may be foreground or background objects. If they're not moving with the cluster, it's sometimes very difficult to tell, particularly if the cluster doesn't have a very well-defined motion. But you eventually end up with something like this. So this is the initial final mass relation. These are all the white dwarfs from these open star clusters. Now, one thing you might notice is that I told you early on that the average mass of a white dwarf is down here at about 0.6 solar masses. And most of these objects are way more massive than that. And this is because the clusters are young. So we're looking for white dwarfs in open star clusters, but the clusters have to be near, they have to be bright. That tends to mean they're young. And if you're finding a white dwarf in an open star cluster, then they tend to be more massive because they have to have evolved into a white dwarf during the lifetime of that star cluster. You can imagine for an object in the Pleiades, so this object here or up here, they only had 125 million years to become a white dwarf. So they're going to have come from a pretty massive star in the first place to have evolved that quickly. More massive stars, they gobble up more fuel really quickly, so they evolve really fast. So the problem we have here is that a lot of our 1 solar mass stars don't fit on here because they haven't evolved yet. The sun's 5 billion years old and it's not evolved into a white dwarf yet. It's only about halfway through its life. So the problem is that while we have this fantastic relationship, it's absolutely useless for lower mass white dwarfs in trying to determine what stars they came from. And this can be a bit of a problem. So yeah, that's what I was just saying. It's effectively some problems to do with using white dwarfs in clusters. Now, Gaia has come along, and this is Gaia's map of the galaxy, which is beautiful. I do like the 2 Magellanic clouds at the bottom there. I have a slightly amusing observing story from when I was observing in South Africa and went out to check the weather and sort of went, oh, the sky is beautiful tonight, absolutely clear, apart from those 2 really awkward clouds over there. That's going to get annoying later on. And then promptly realized what exactly, they're called the Magellanic clouds for a reason, Sarah. But yes, this is Gaia's view of our galaxy. So Gaia has provided parallax for a huge amount of white dwarfs. I think we're up to 20,000 now, but it doesn't measure their line of sight velocity, what we'd call the radial velocity, because Gaia is only doing it at a certain way. It's doing it based on calcium lines, which appear in most main sequence stars, but not in white dwarfs. But we can combine the proper motion, so that's the RA and the deck motion over time, and the parallax, the distance, to figure out where the white dwarf is in space, whether it does belong to these clusters or not, and also to try to get the age of a white dwarf. Maybe it belongs to these sort of loosely bound moving groups, or we can at least tell if it's part of the thick disk or the thin disk of the galaxy and get an age estimate that way. And that will give us a wider range of masses than the clusters currently allow. And it also works for the magnetic white dwarfs because we don't have to directly measure the temperature and radial velocity, which is a nightmare because of their lines looking like this instead of like this. Okay, I'm going to pause here. Does anyone have any questions? And I guess the next question is, I think I've been talking for about half an hour, so do you want me to continue or do you want me to stop would be the next question.
Well, no, Sarah, we can continue. We'll just have a quick poll and see if anybody's got a question. Sure. So can you electronically put your hand up if you've got a question?
Well, in fact, you've already kind of partly answered what I was going to ask by talking about white dwarfs in clusters. I'm just wondering how many white dwarfs are found in things like OB associations, because they tend to produce, much more massive stars, don't they, which are going to evolve a lot quicker.
I don't know, but my feeling is that most of the nearby OB associations are very young. I'm thinking of things like Upper Sco. And they're only a few million years, like 10 million years. So they're not old enough to have formed the white dwarfs yet.
Right. That's what I was thought. And you've just sort of confirmed it. I mean, lovely. Thank you.
Globular clusters are the place to look, but they're so dense and they're so faint and they're so far away that it makes life extremely difficult.
Okay, thank you, Michael. Is there anybody else who's got a question?
I've got a quick question. Thickness of white dwarf atmospheres. Sarah, can you remind us how thick they are? I expect with the gravitational field strength being quite intense, it won't be very much. Oh,
goodness. I can't off the top of my head. So the radius of a white dwarf is about that of the Earth. So that's about 1 × 10⁻³ solar radii. It's about 100, about 100th of the solar radii. And the atmospheres are then possibly 1/10 to 100th of that again. So they are not thick.
Probably a few kilometers.
Thick, but we don't actually know how thick they are. And of course, that's where all the stuff to do with the metals, that's where all this stuff is hanging around.
Okay, Peter.
Thank you.
Okay. So, Sarah, could I ask you to continue, please?
Sure. So this is the stuff that I work on, white dwarfs and brown dwarfs. So how are you all with brown dwarfs? I'm going to ask you guys a question.
We're familiar with them. The gentleman you've been talking to, Peter, he hunts them down at the moment. So
I think Jackie came and talked to you at one point as well. Is that right? Yeah.
She did.
Okay, so as a quick refresher for anybody who doesn't know, brown dwarfs are objects that form like stars, but they never get massive enough to fuse hydrogen into helium. So your gas cloud collapses and they're the remnants that are left over. They get hot, but not hot enough to burn anything. And once they're formed, they cool and fade away. So they have temperatures of about maybe 2,500 down to almost like 400, 500 Kelvin at the really cool end. Okay, now white dwarf, brown dwarf systems, which is what I look for, are extremely rare. So only about 0.5% of stars have a close brown dwarf companion. This is called the brown dwarf desert. And you can see it here on this figure. So these are all the planets, which are about Jupiter-sized hot Jupiters around main sequence stars within 3 or 4 AU. And these are your stars. And there's basically about 20 brown dwarfs that sit in this gap here. Literally 20 in our galaxy that we know about, compared to a few thousand planets. And you'd think that we might find them quite often because they're physically Jupiter-sized, so they look like a hot Jupiter. They transit in front of a star. But it turns out that actually they are just intrinsically rare. And this is because it's really hard to form something little next to something really big. So when you're forming your planet forms from the disk around the star. So that sort of works. But when you're forming your brown dwarf orbiting a star, you have to form them both from a gas cloud, and you have to have your little remnant next to your big star, and your little remnant doesn't get accreted onto the big star. So you can see why this might be quite difficult. Binary star formation tends to pull towards equal mass binaries. You get two things that look the same. So this huge ratio between your brown dwarf and your main sequence star is really quite unusual. So you can imagine to end up with the evolved form of that, the white dwarf brown dwarf system is rarer still, because there's going to be a percentage of brown dwarfs that don't survive the death of their star. Now, there are two main types. These are those discovered via what we would call common proper motion. And this is what Peter's been working with me on. And those discovered through an infrared access. So in those cases, they're objects generally where we know there is a white dwarf. And when we've gone to observe it in the infrared, we've gone, ooh, well, that's a lot brighter than it should be. And that's because it has a brown dwarf companion. Okay, so I've covered this. I'm not going to go through it again. I'd forgotten I put that slide in. So this is WD 0806 minus 661. We do like our telephone numbers. But this is your white dwarf, and this is the brown dwarf, and this is one of the coolest, if not the coolest, brown dwarf known yet. It's got to be probably a white dwarf, and it's about 6 Jupiters in mass, and the whole thing is a few gig years old. And these two were discovered in, this is the Spitzer infrared image, and they move together through the sky. So once you have the measurements of the movement of one and the measurements of movement of the other, you can then watch them move together over time. And these things are in sort of a few thousand-year orbits. They're separated by tens of thousands of AU. They're massively, massively widely separated. Alternatively, there are nearer by objects where the brown dwarf and the white dwarf are quite often what we would call blended in an image. So you look at it and there's two objects there, but you can't quite separate them. This is where you need fancy adaptive optics or something like that on Keck to do this, where you can take into account the wobble of the atmosphere to pull it apart. But yeah, this is a white dwarf and a brown dwarf, and this is actually Peter's discovery. So this is an object that Peter's found as part of Backyard Worlds, and we hope to get some spectra and some follow-up of it soon, particularly to confirm what type of brown dwarf the red bit is. So it's likely to be an early type brown dwarf, what we would call an L dwarf, which is dominated by clouds, as opposed to a later type object where the clouds have sunk below the photosphere and you've got sort of a methane-y atmosphere. But this is pretty cool. When you think that of these objects, there are maybe only 10. I think there's only been 4 or 5 of these published to date. So you guys are pretty special having Peter who's discovered a new one. Okay, so the objects that I study are closer still. They're not resolvable. And my binaries have brown dwarfs that have survived the death of the white dwarf, but unlike the previous 2 systems, which have either been unaffected or the brown dwarf has been pushed outwards, you can imagine as the star expands to become a giant, a low mass object on the edge of that sort of gets pushed outwards like a surfer on a wave. These objects, the brown dwarf has ended up being completely engulfed. So the stars swallowed the brown dwarf, and to conserve angular momentum, the brown dwarf spiraled in, and then at some point before it's hit the core, the envelope's been ejected, and you're left with your white dwarf and your brown dwarf in a very close binary. So these objects that I study have periods between 10 hours, and the shortest one I've discovered is 68 minutes. So these are, if you imagine, so Hubble goes around the Earth, which is about the size of a white dwarf, once every 90 minutes, which is about average for these systems. So if you put Jupiter on the Hubble Space Telescope's orbit, that's essentially what I am looking at. So they're tidally locked. One side of the brown dwarf continually faces the white dwarf, so much like the Earth Moon. And you can imagine that your white dwarf could be extremely hot, 20,000 Kelvin, 30,000 Kelvin, and it's continually irradiating this one side of the brown dwarf and heating it up. But the other side continually faces space. So you then get energy transport from the day to the night side. You get winds and jets and all sorts of exciting things happening with the clouds and the atmosphere. Okay, so when I observe them, this is generally what they look like. These are light curves. So I'm just measuring the brightness of the star, brightness of the combined system over time as we go around the orbit. And the letters are the different wavelengths we use. So this is, J is about 1.2 microns, H is 1.4 microns, and K is 2 microns. So this is the near infrared. These over here at the bottom are the mid infrared from space. But I'm looking and measuring the brightness of the system over time. Now the white dwarf brightness isn't changing. The white dwarf is constant. So what I'm looking at is the night side or the dark side of the brown dwarf, and then I can watch it get brighter, and then I watch the day side, and then it gets fainter again. So that's about a 0.4 magnitude difference between the day and the night side. And this increases as I go to longer wavelengths, which tells me something about the brown dwarf atmosphere, that the mainly UV radiation that's coming in on the day side is then having a large effect on the part of the brown dwarf atmosphere that we see in the mid-infrared, and this is due to the clouds and the composition of the atmosphere. What this looks like when I take spectra is this. I really do love this. So I've taken out the white dwarf motion. This here is the white dwarf. This is, it's what we'd call a trail spectra. So each one of these each one of these sort of pixels is a spectrum taken over time, and I've just stacked them up over the orbit. So, and then I've taken out the white dwarf motion. So this straight line is the white dwarf absorption feature, which just sits there because I've taken out the small motion of the white dwarf. This is the emission feature. So this is the hydrogen from the surface of the brown dwarf that's being excited, and I can watch it move. So it comes all the way up here. So if we start here, so this is the night side. You can barely see any emission from the night side. That's the cool side. And then as the day side comes into view, it gets brighter and brighter and brighter and brighter. And then again, it fades away. And we have 3 or 4 objects where we can see this. So these are all different white dwarfs, different temperatures. I love these figures because you can literally imagine what's going on in the white dwarf atmosphere as you see it, and you see as the day side comes into view, things start glowing and looking brighter, and then as you see the night side, it all fades away again. But what I've also been able to look at, taking us back to the white dwarf mass radius relation, is what happens when you look at these brown dwarfs and try to determine what on earth all this radiation you're pouring in on the day side is actually doing. So all of these are, this is the mass across the bottom and the radius at the side for all the known brown dwarfs orbiting main sequence stars and white dwarfs. So the white dwarf ones are here, this one and this one and this one. The color of the point is related to the temperature of the host star. So the red ones, this one, this one, this one, these are all M dwarfs. And then we go up to G stars and slightly higher, and then you have the white dwarfs up here at the top end. Now, most of these orbit F, G, or K stars because they've been found by planetary searchers, and most planet searchers early on were looking for planetary systems like our own. So we were looking for Earth's orbiting FGK stars. Of course, what we didn't find that. We found Jupiter's orbiting FGK stars on orbits of a few days. That, I think, was not what anybody expected. But the brown dwarfs are the same. So because the brown dwarfs were found from these surveys, they mainly orbit solar-like stars. We don't know of many orbiting massively evolved stars. There are a couple around A stars. We know of 3 that are eclipsing white dwarfs. So this one here, I showed you the spectrum of on the previous slide. This is a 24,000 Kelvin white dwarf. It's extremely hot. It's very old, and it's orbiting a brown dwarf in a 72-minute orbit. But interestingly enough, the brown dwarf it's not inflated. All that heat is not doing anything to the brown dwarf at all. It's exactly the radius you would expect from its model. So the size of these points is related to how much irradiation the brown dwarf is getting. So, you know, you've got an M dwarf here. It's not really getting irradiated a lot. Maybe it's quite far away from its host star. This is getting a huge amount of irradiation, but it's not inflated. But then you have this collection of odd objects here. So this one is inflated. This one is inflated. So this one is orbiting a 10,000 Kelvin white dwarf in 2.5 hours. This is 100 minutes around a 7,000 Kelvin white dwarf. And these two are orbiting main sequence stars, but they're orbiting active main sequence stars, stars that are known to be more magnetic. They have spots and they flare. So we don't really know what's going on, to be honest with you. This is the story of my astronomy life in general. I find a new system, and there are only 9 of these close binaries, and they all look completely different. But looking at this, so at the lower mass end here, it looks like it doesn't really matter. If you have a mass of less than about 35 Jupiters, it doesn't really matter how much irradiation you're getting. The brown dwarf is quite easy to inflate. And this happens with exoplanets. We see lower mass hot Jupiters are really easy to inflate. And then everything sort of seems to fit, apart from these objects that perhaps orbit the more magnetic stars, which is interesting because these stars are also going to flare. So these are the stars that are also going to be perhaps more likely to interact with the brown dwarfs or any planets that are there. They're flaring, they might have coronal ejections and they might have excessive winds, all this sort of stuff that when they interact with their white dwarf, they are going to affect its atmosphere in ways that are perhaps a little bit unusual and a little bit more unusual than we see in the other systems. Perhaps these are the white dwarfs. If we want to look for aurora like we see in Jupiter or Saturn, these maybe are the objects we want to be looking at. So this is sort of the most exciting thing I've been doing at the moment, is looking at trying to pick apart what effects the irradiation has on the atmosphere of these objects. They're quite difficult to observe directly because, as you can imagine, the white dwarf is quite bright and the brown dwarf is quite faint. And we have to observe in as long a wavelength as we can, which is tricky from the Earth because the Earth's atmosphere is full of lines that glow at this wavelength, which is somewhat annoying. So again, we're waiting for James Webb to be able to observe these directly and block out the light from the white dwarf to be able to actually understand what's going on in the atmosphere of these things. Okay, I am going to stop there. Well, thank you very much for listening to me rabbit on at you, really.
Thank you very much, Sarah. There was loads of information, and yeah, sort of white dwarfs are never going to be the same for me.
No.
And ladies and gentlemen, so usual routine. If we are going to ask questions, I will nominate you to unmute your microphone, and then you can ask your question. Sarah, can you unmute your microphone as well? Thank you. So Roy Gunson first, please. Roy?
Hi there. While you were talking, what I was wondering was that when the star turns into a white dwarf, I mean, there's a mass ejection. If there's a, say, planet Jupiter plus in that system at a fair distance, is it possible that that's going to gather material and turn itself into a brown dwarf?
That's a really good question. So I think the answer is likely to be no, simply because the envelope of these stars is way less dense than you generally think it is. If you think you are putting something Earth-sized where the sun is, and then you're filling between the sun and Mars with just under half a solar mass of material. That material is not massively dense. It's really quite sort of loose and well, gassy. And you then put something that's the size of Jupiter in there, and it doesn't spend very long in there, maybe 1,000 years at most. So it's not really got a lot of time to gather a huge amount of mass. But what we do see for the cataclysmic variables that I talked about is that we see some of those where there's a white dwarf with a brown dwarf companion. And we think that what's happened in a lot of those is that the brown dwarf was originally an M star, a red dwarf, and it's lost mass that's put it underneath the 70 Jupiter sort of limit for burning. And it's become a brown dwarf because it's lost an excessive amount of mass to its companion.
Okay, Roy.
That's fine, yeah.
Can I ask Peter Lloyd if he'll turn on his microphone?
Thank you. Yes, thank you, Sarah. I'm puzzled a little bit by the binary between a white dwarf and a brown dwarf. Did I understand it correctly? The brown dwarf is actually bigger than the white dwarf.
Yep. Yeah.
Right. So I did get that right. And did you also imply that at an earlier phase, when the white dwarf, before the white dwarf becomes a white dwarf, when it's this bloated star, the brown dwarf is actually orbiting within that star?
Yeah.
And it can do. I'm just amazed that it can do that. You would think there would be so much material there, it would drag it down to the middle in next to no time at all.
Well, so this is it. So the envelope is not massively dense, as I was saying to Roy. So you have this it's a lot of mass, half a solar mass, but you're fitting it between us and Mars, and between the sun and Mars. So it's not that dense. But there's also, and again, this is called common envelope theory, and it's hard to model, as you might imagine. But there's also a theory that if you perturb that envelope with something that's big enough, you can prematurely cause the envelope to be ejected. And that's perhaps why a lot of these in a lot of these brown dwarf, white dwarf binaries, the white dwarf is really low mass. It's like 0.4 solar masses. And we can't form that by getting to the end of a star's life. You can't have that lower mass star become a white dwarf of that. So essentially it's a bit, I'm trying to think of a good analogy, but essentially you have your big wobbly giant, and by engulfing the brown dwarf, that causes the envelope to eject earlier than it normally would have done. So
sort of slingshot effect.
Yeah, so you end up with this very low mass white dwarf orbiting the brown dwarf. Whereas if you'd have left the system alone and the brown dwarf wasn't there, the white dwarf would have been much more higher mass because there would have been more stuff pouring onto the core.
Thank you.
Okay, Peter.
Yes, thank you.
All right. So have we, Andy Devey, can you unmute your microphone? Okay, Andy.
It's just a question. You've obviously not been able to observe white dwarfs for very long, but have you been able to notice any that are actually accreting material where you can see a measurable change in the mass, and anything that's getting close to the 1.4 limit, solar mass limit?
So a lot of the white dwarfs that I observe are, as I was saying, are the lower mass objects. But yeah, I think there are white dwarfs, particularly those in cataclysmic variables, where we know they are interacting. We see emission lines and we see the disks, and they tend to be higher mass white dwarfs to start off with because they've evolved quickly enough to have their close companion that's accreting mass onto them. However, they're quite difficult to observe to get, if you imagine, to try and get an unblemished look at the white dwarf, because quite often you have this big disk of material that comes around the white dwarf, and that's full of emission lines, and it also quite often gives us sort of big humps of emission to do with how fast the electrons and everything are moving around the disk. So actually getting that nice sort of unblemished DA spectrum of the white dwarf is really, really difficult. And what we tend to do is observe those sort of systems in the X-ray, and then work out the accretion rate and try to work backwards from the mass of the secondary star, so the mass of the star that's losing mass, as to what sort of mass the white dwarf must have been. But quite often these form novae, and they sort of, you know, burp out huge amounts of mass, and then they settle back down again to a lower state. And if you observe them, they're quite often active at a very low level. They flicker just because of all this material that's landing on them.
Okay, thank you.
Okay, anybody else got a question? I do not see anybody's hand up electronically or visually. So I think you've hold on, there's some, oh, it's just a bit of nose scratching, that's all, Sarah. So what we'll do, we'll end this part of the evening's meeting with our usual thanks, please. Can we give a big Mexican Swinton Astronomical Society? Thank you.
Thank you very much.